I have to admit that I have not prepared very well for this talk because I wanted to improvise to some extent and also wanted to show you some things that hopefully you will find interesting. I don't know how it will come out in the video. Also, I will share some of my experiences in using Erlang OTP for parallelization and trying to see a bit how it can improve, or what's the current situation is, what possibly are bottlenecks, and what can be improved. And I'm glad to say that actually we have found some bottlenecks, but we are improving them as we speak. And hopefully you will not notice them before they get fixed. This is all done in the context of an EU project that we started relatively recently. It says there that it started officially in October 2011, but in reality, the kickoff meeting was in the 1st of November of that month, just before the Erlang factory in Stockholm, for those who were fortunate enough to be there. And it's supposed to continue for the next 2.5 years from now, ending in September of 2014. We have a pretty good team assembled. We have Ericsson on board, Erlang Solutions, who is hosting this event, Électricité de France, they are using Erlang for some big simulations of things that I'm not allowed to talk about. And we have 4 academic partners, 2 in the UK, the Heriot-Watt University and the University of Kent, and Uppsala University and the National Technical University of Athens. Actually, it's a research center there. So the goals of the release project is to scale Erlang's concurrency-oriented programming paradigm and build reliable general-purpose software, such as server-based systems, on massively parallel machines. So we aim to target at some point machines with hundreds of thousands of cores. Clearly, we're going to go into the 10,000s of cores in the lifetime of the project, but hopefully we're going to make changes both to the language and to the runtime system that will allow Erlang to scale in that number of cores. So we want to investigate language primitives for scalable distribution. So especially our partners in Heriot-Watt University are leading that effort on the distribution part. The effort that I am leading is the virtual machine extensions and improvements, and we are working very closely with Ericsson on that part. The effort that the University of Kent, with Simon sitting there, leading that effort, is to create tools for parallelizing and refactoring existing code. Also tools for profiling and testing for errors, and the testing for errors is more my part, I guess. The part of Erlang Solutions is to build scalable virtualization infrastructure and investigate what are good alternatives in that respect. And we have one part so that we actually go towards the so many cores together with Électricité de France on porting Erlang OTP to the Blue Gene architecture. And actually they have more than one Blue Gene machine. And they are located in Paris, so I'll definitely be, I would be doing that anyway, but it's very nice that they are located in such a nice place. So that's pretty much what the release is about. And what is this talk about, really? I wish I knew, but what it is about is to investigate the scalability of Erlang OTP as it is today, start from today's baseline in some sense, and see where are the bottlenecks and how we can detect as many of them, and how we can possibly improve the situation. And we started on multi-core machines, no distribution right now. The idea is that we are going to also include benchmarks that have a part of distribution that also run on multiple machines. But for the time being, we are concentrating on big multi-core machines. Both the type of machines that you will have on your desktop, a typical 8-core machine or 4-core with hyper-threading machine that many of you might have on their desktop, or at least the fortunate ones. And on also big multi-core machines, and I will show you some numbers from a big multi-core machine right now. Also, this talk is about reporting something that we have been working for the last 3 months on our effort to parallelize dialyzer as a concrete, non-trivial application of Erlang, something that has about 30,000 lines of code, and how you can parallelize such a code base. And I will share with you some experience and lessons learned. Some of them are frightening, so I don't know what will happen with the video afterwards, but anyway. And show some performance numbers. And also give a sneak preview of the planned and future VM improvements for Erlang OTP, some of the things we are doing. I don't have them written, but I will tell you what we're doing right now. And finally, and most importantly, I want to ask you for your involvement. I want benchmarks that if you have scalability needs and you have something that you can share with us, either in the public domain or in a place, I can guarantee that if you give me a benchmark that you don't want to share with the rest of the world, I can guarantee that will not be shared with the rest of the world. Hopefully, there will not be that many of those. Most of you can probably distill the interesting part of your application in something that we can share with others. Anyway, without further ado, let me go to the first part. So we have created, or actually we got from Erlang OTP team, a set of 14 concurrent programs that have been used for quite a while for benchmarking of the SMP implementation. And we turned them into scalability benchmarks, really. Benchmarks that measure the performance improvement or degradation, hopefully not degradation, as the number of cores increases. And we are currently running them on 3 platforms in a relatively new i7 with 4 cores and 8 logical threads. A 4-year-old Xeon server with 16 cores, and a brand new AMD Bulldozer type of machine server with 64 cores. It has 4 CPUs with 16 cores each. So I will only show some of the numbers that we have from the first one and the last one to show you the 2 extremes, I guess. And there is a technical report that for those of you that are interested to see the rest of the numbers. By the way, our intention is that all of these things will be public. So we have a site for release where these things actually are there, but we have to polish them a bit. But hopefully pretty soon you will be able to actually access them and play with them if you are interested. So out of these 14 concurrent programs, I will just show you 4 of them and how they behave as you increase the number of cores and schedulers of the Erlang VM from 1 to the max number of cores that or threads actually, that the machine can accommodate. So that's one of them. It's called the Erlang Hackbench on an i7. Remember, this is a machine with 4 physical cores and 8 threads. So we are starting the VM with 1 to 8 schedulers. And we are measuring the speed ups that we get as running exactly the same work, actually 4 of them here, on the virtual machine running with from 1 to 8 schedulers. And actually you can see that this is a good case pretty much here. We get close to linear speed ups, very, very good speed ups, up to 3.4 or something like that on a 4 physical core machine. And then, of course, with the hyperthreading, you cannot expect to get really linear speed up above that. This is not a singleton. Oops. Sorry? They are different. They are different. It's a different workload. So I don't remember. You remember, Richard, what they are? Okay. It's parameter to the test.
How many times and how many processes or something like that.
Yeah. But these numbers are actually more than the number of schedulers there are. So we are starting that many processes and sending messages or something like that. There is Mandelbrot, which also shows pretty much the same behavior here, up to 4 cores. We have pretty much perfect speed up. And above that, the machine cannot handle this sort of thing anymore. As I said, it's just a 4-core machine. Not everything really looks so nice here, and I will show you one that, oh, actually there is another one, random thingy, that also shows pretty much the same behavior. There are things that involve the edge tables, where you can see some very different situation. The one is here, and when you start on a small number of schedulers, you get some small speed ups. But as you have more and more processes trying to access the same edge table, there is even a degradation in the performance. So this is one of the things that we have actually written down as an improvement, that we are going to specifically look at the performance of edge on big multi-core machines in the proposal. And I'm very glad that it wasn't just something that I dreamed up as a possible problem, but it's actually something that needs to improve. Yes?
How does this interact with some of the edge options to optimize for read load?
Okay, so yes, we are actually measuring these too, and there will be a report. The first deliverable in the work package that we have will be the report, and we are actually measuring the read concurrency options, and one more, I think, I don't remember which one. I don't have this number right now, but in this particular benchmark, they don't help very, very much, because there is even a degradation as you increase the number of schedulers. Yeah.
Well, I have to say that that's what you get when you have shared memory. Actually, I mean, locking in shared memory, this is what you get.
Sorry, these are just, in some sense, synthetic benchmarks. Okay, they measure specific things. So they are not real applications. In real applications, you will have some part that is accessing edge tables. You will have some parts that are doing hopefully independent computation in your processes, you will have a mix of these things. And this is actually the next step. We want to actually measure real applications. But measuring real applications means that somebody who actually has the real applications has to send them to us. Because otherwise we are not going to be measuring real applications, we're going to be measuring made up applications that we dream of. Now, how do these things look when we go to the big machine, to the bulldozer machine that has many schedulers, where we can start the system from 1 to 64 schedulers? And you can see that we get some better speedups in the beginning, up to 16, 17, 18, 20 perhaps cores. But after that, things start to flatten out. And this is not particularly atypical. You get this sort of behavior in most real applications. You will have some sequential part, and Amdahl's law will bite you in these cases. The same thing can be seen on, oh, actually, let's see what happens on Mandelbrot, and I will do a demo right now. I will just try to connect on the machine. And here it is. Unfortunately, my dear student is also running some things, as you see here. He's, yeah, this is Friday night in Sweden. You run benchmarks like that. So, but let me run it. Perhaps this is too small for you to see. Let me make it bigger. So I will just keep that one there so that you see the processors working. Huh? No, I will tell you what this is. So let's say start with 4 schedulers first. And let's run Mandelbrot. Actually, let's compile this to be sure that it's the new one. It's actually in native code. This is, I have put a, this is one of the, well, it doesn't really matter. As far as scalability is concerned, you get the same results whether you run on native code or not. But it just so happens that this particular benchmark is running at 8 to 10 times faster at least on native code. So I have actually put compile native code as a attribute in the file to make sure that this is actually running native code. But as far as scalability is concerned, it's the same thing. So I can run this sort of thing, some numbers, 400 and 200, and unfortunately you cannot see which ones they are there, ours, and which ones are my students. But we will get a number here, and this is the interesting part. So now 4 of them are clearly mine. We started the system with 4 schedulers. And we will get, it's 23,700 something. This is the time that it takes to finish this. So now let's exit here and run this again now with 8 schedulers. I don't need to compile now. So the previous time was 23,000 something. Let's see how this will work on double the amount of schedulers. 12,681, so it's pretty good. Let's see on 16. And you will see now at some point 16 of them going on there. And actually, one nice thing is you see them, they are all green. It means that this is actually very, very, very nicely parallelizable. I don't know whether you know this particular tool. It's called HTOP. I very much recommend it to everybody. It's really, really, really nice. It's a replacement for TOP. It's an open source thing. You can get it as a package in most Unix distributions. So now the time is actually a bit less than half. Before it was 12,681. Now it's 6,200 something. And just for fun, let's start it once more with 32 cores. This will be very fast. We're just going to see them there being flashed, and it's 3,400 something. So you can see that in some cases where you have really independent computation, the base of the virtual machine has actually been programmed and has all the right components to execute this thing very, very fast and without really any bottlenecks at all. The numbers here, I'm running on a size of 400 of the image, and I'm running with 200 processes. So the processes here are more than the number of schedulers. And it's, of course, not perfectly balanced. It's not a divisible number by 16 or any power of 2, actually, other than 2 or 4 and such. So, back to the presentation. There are other benchmarks that don't behave as well, as good as. So actually, Mandelbrot is one of the benchmarks that we would get something like 40 to 45 times speed up on 60 to 64 cores. So it's actually a very, very nice benchmark. I wish that all of them were like that. Not everything is like that. If you have a bit of sharing and contention, you will get something like that. In many cases, you will get a speed up that reaches at most 8, even if you are running on a big multi-core machine. And of course, if you have ETS, you will get things like this one. The one is there. Okay, by the way, ETS is very nice for some things, which actually brings me to my next one. Our experience is on Dialyzer. So Dialyzer, for those of you that don't know, it's a tool that analyzes source code. If you have a small code base, it works pretty fast and it's actually very effective. If you have a big code base, it's even more effective because it finds many more things that you probably have overlooked, but it's actually slow. So if we're analyzing the whole Erlang OTP on this machine that I just showed you, it consists of more than 1.5 million lines of code, Erlang code. And in the sequential version, or actually the version that is in R15, it takes on this machine 83 minutes. And building a big PLT, persistent lookup table for a standard lib kernel and some more applications that are important, it takes 26 minutes on the sequential version. So we wanted to parallelize this. This is a big application. It's completely written in Erlang, so we thought that this would be a relatively easy thing to do. The bad news is that actually there is state data that's passed around. The code was written in a very nice functional style where you are passing an extra argument which has the state around. And this works very, very nicely when you are executing sequential code in Erlang. Why is that? Because when you call something, when you call a function, you just, and this executes in the same process, you just pass a pointer to the extra argument that you have already in your heap, most probably. So you just pass a pointer to the heap, and it's very nice, very, it works very, very well. So how do you parallelize code that in pretty much all languages? So what do you do? What's the basic thing to do to parallelize code in Erlang? You spawn. Unfortunately, there are many people that don't realize that spawning is actually something that has a cost, because you have to actually, now you cannot pass a pointer to the data, to the arguments anymore. You have to literally copy the arguments to the process that you are creating. So now you change the cost of the function call from just constant time or proportional to the number of arguments. Now you change it proportionally to the size of the arguments. And if you are passing around big data structures, you need to traverse them. And actually, the current implementation doesn't just traverse them once, it traverses them more than once for good reasons. But it also does something which is even worse. It actually expands these terms in the case where there is sharing. So our first attempt to parallelize dialyzer resulted in a nightmare. We just added a spawn statement, and this is actually probably the part of the video that has to be edited out. This is not a joke. Unfortunately, this is not a joke. We added a spawn statement on one place in the code where we wanted to spawn the analysis function for each of the functions that we were analyzing, or the modules, or whatever, it doesn't really matter. And we experienced something that looked like an infinite loop. Because something that was running in literally a minute hadn't finished after 1 hour. So that's my definition of an infinite loop. So I said, something is wrong here. Actually, it was my student Stavros that had that. So it was actually a very similar situation to this one. He started doing this on a Friday evening, and he did it at home. So he thought that something is wrong in his laptop, or the connection is problematic. So he actually was working on it all the weekend. And on Monday he comes, sorry, you have to see this. There is an infinite loop here. I said, okay, but have you tried debugging this at all? Or just, I said, debugging, what is this? He answered. He asked me, this is a joke. And I said, okay, did you put an I/O format somewhere? Because that's how I debug things. So we took out the spawn and put an I/O format in one particular line that I can show you in Dialyzer's code. And guess what? Can you guess?
Just on a lot of information, I mean, you just see this single line.
We experienced the same infinite loop. So we took out the spawn and we put an I/O format. And we experienced the same thing that looked like an infinite loop. So at that time, I called Bjorn Gustafsson at the Erlang OTP team and said, Bjorn, you have to see this. Just add an IO format on that line. So he said, OK, I'll take a look. And he found it also interesting, I guess, and he showed it to, actually he told me something else at that time, which solved the problem. He said, oh, don't use IO format, use Erlang display. And Erlang display worked. IO format, where IO format did not work. So he actually showed it to Patrick. That's what I think, right? And Patrick actually found the problem.
No, he did.
Ah, he did.
I just stood there and said, no, it's bug.
So to make the long story short, what happens is that if you're using IO format, you send the data to some other process, which actually copies the data to the other process. So the data was the state, this state that we were trying to parallelize, was something that was in the order of some megabytes. I don't really remember the exact size, but say, let's say 20 megabytes for just to give you some idea. So what was happening is that this was a term that had a lot of sharing. And when we were trying to print it using IO format, all this sharing was expanding. And guess what? It came to some gigabytes of memory. I actually left it running. Can you guess how much time it ran before it actually printed the term? Not the whole term, I just put to print some part of the term. No, because you can do that. Anybody who wants to guess? 26 hours. Just to print the topmost 5 levels of the term. 26 hours, because it has to copy this term from one point to the other. Now, it so happens that actually this was a case that we could fix the problem because what we were passing was the whole state, but in the function that we were passing it in the closure actually that we were passing it in as an extra argument or as a implied argument actually, it was only using parts of the state. This is a typical situation. Think of some structure or some record that you are passing as an argument, and in the function itself, you don't use the whole term, but only some fields of this record or this structure. If you are lazy, you might not pass the individual pointers to these fields, but you might pass the whole term. So once we changed that, it was a one-line change. Actually, it was, this is the thing that actually amazed me. Was it Bjorn that found this or you? The problem is that this was literally 1,200 lines away from, in the same file, but 1,200 lines away from the IO format and the spawn. So anyway, so after we fixed that problem, actually the parallelization of dialyzer was relatively smooth, modulo finding some issues in some of the standard libraries. And this is a typical situation. Once you start parallelizing some code, you discover all the sequential bottlenecks that you have in your system, and you never thought you had them. Because what's happening is that the the code that you parallelize now suddenly becomes really, really fast, and your bottlenecks are what you haven't parallelized, because you thought that this was really going to be executing very fast. And this is the point that I'm going to show you how, actually let me take one more just to give you some idea, this is a very, very high level description of how dialyzer works, so that you understand what I'll show you. Obviously, dialyzer has about 30,000 lines of code, and this is what it boils down to. We initialize the state given the input, and the input here is the number of files that we want to analyze, and we put them in the state. The state will contain information about all the code that we have, all the type declarations that this code might have, all the records that it has, all the external types, various things related to the code. And this is the state we have to pass around. This state will have also something that will have the types that we try to infer, that we're also going to store there. So while we haven't reached a fixed point, meaning that we have not found all the information that we are interested in the analysis, we find types. This is an analysis that goes bottom up. It goes from the functions that don't depend on any other functions up to the exported functions of the module or the application. And then we refine them based on usage within the module. So there is an analysis that goes bottom up, and then an analysis that goes top down to infer these types. And once we do some fixed point computation here, while we are finding more and more information, and we have not reached the fixed point, we do this sort of thing. This might repeat some number of iterations. And once we have found all these things, all the types, we might be generating warnings. We might be, because we might be just building the PLT to store the type information. If we build the PLT, we don't generate warnings. If we run dialyzer just to generate the warnings, we will do that sort of thing. So that's actually the idea of how dialyzer works. So let me show you now on my laptop how I've run dialyzer here on a bunch of applications. Actually, I run this script, which analyzes ASN1, edoc, ERTS, compiler, crypto, dialyzer, inets, hype, you can read. It's a bunch of 20 applications pretty much. This is a sequential version of dialyzer. And I've run it with one scheduler. And you can see here what happens. These are all the phases that it does. It compiled all the files. There were 922 modules in total. It then cleaned up the call graph. It found remote types. It did some ordering so that it starts the type inference here, which analyzed that many strongly connected components. Strongly connected components are possibly functions that are calling each other mutually recursive. So there are at least that many functions that are being analyzed. Then it ordered this so that it does the refinement in the top-down fashion. And then it did another thing like that. For some of these SECs, we have found all the types that we can infer. So we don't consider them anymore in the analysis. For the remaining ones, we have to do the analysis again. It turns out that out of the 53,000 strongly connected components, the 43,000 approximately need to be reanalyzed. We are doing the refinement, and then we do one more type sig here. You can see that most of the strongly connected components, we have found type information, but there are 1,539 which we still need to analyze. And hopefully we reach the fixed point here, and that's what's happening. And this is the time that it takes to write the PLT in the system, in the file system. So this is just to give you an idea of how this works on just one core. And I will run it now with 8 cores here. My machine only has 4 physical cores, but it has hyper-threading. So we're going to be looking at it while it works. And actually, I have h-stop here. And this is the interesting part of h-stop. So the compilation, what it does, it compiles all the files to core Erlang. And already you can see that this took just 12 seconds when it took, what was it before? I've lost it anyway. So the first type sig here took 300 something seconds. Let's see how much it will take now. And let's see if we have good utilization. You will see here that it's pretty good, the utilization right now. All the green things means we are doing, the green thing is very good, okay? It's, the red thing means that there is some system time there, most probably due to ETS. We are using ETS tables here because we are storing both the code in the ETS tables and the types that we are inferring. But we are using them in a relatively nice way. We are using them really as a database. But of course, there is some cost. But you can see that actually there is a very nicely parallelizable problem here. We get, now we are running out of work at this point because we have analyzed pretty much most of the functions. And it has finished. It has finished now in 86 seconds, where it took 303 seconds before. And now we are doing the refinement. And still, you can see this one is also very nicely parallelizable. To make the long story short, on this 4-core machine, I think I will get something like 2.5 to 3 times faster, or a bit more. It took 15 minutes and something before. Now this will finish in, I think, something more than 4. Okay, yeah. Let me, just out of curiosity, let's see how this will work. The second type sig, by the way, you will notice that even though it analyzes less strongly connected components, it takes more than the first one. And the reason for that is that now we have inferred type information, and we are working with big types, with big structures. While in the first iteration, we only had very small types to work with. So let me skip this, and we'll show one at the end of the talk. I will just skip this part. And let's go directly to the speed ups that we get. This is the speed ups of the individual phases. I hope that the colors are visible. The 2 important ones are the 2 red ones, which are the type sig analysis that take a lot of time. And there is one here in the middle, the black one, which is the total speed up, while the other ones are just the individual phases. So we have parallelized all the phases, and up to 4 schedulers, we get pretty good. Up to 4 schedulers, we get very good speed ups. And then, of course, it's the hyper-threading. You cannot expect to get linear speed up at that time. But even with hyperthreading, it actually works. It improves. The same thing on the big machine. There we get speed ups up to, overall up to 8, 9 times. 8 times, I guess, here, 7.5, something. The two big phases, they have better overall speed up, but still, in this machine, you cannot expect something above the 30 schedulers. It also has to do with the memory architecture of this machine. It has very little, given related to the number of cores, it has very little level 2 and level 3 cache. Now, let's go back and see if this has finished and how much time it took. It has finished in 4 minutes, 50 seconds, when it was taking 15 something before. Yeah, anyway. So I'm running out of time, so I will stop here to take some questions. I can say that as part of what we are doing, we have identified some of the bottlenecks. I've already talked to about one of them, the preserving the sharing when you are sending terms across processes and hopefully also across nodes. And we are working on this, and I think we have a very, very good solution, which we are actually benchmarking right now. And hopefully this will not be an issue in future OTP versions. We have identified some other smaller bottlenecks that I probably should not speak right now about them. There is a big issue with the libraries. Some of the libraries have been written long before the multicore era existed. So they are mostly sequential. So if you want to use something that takes a lot of time in some library, it's very difficult, as Erlang is today, to parallelize it. You have to do it yourself. What else? The last thing I want to say is please send us your experiences, and more importantly, send us benchmarks to include in this benchmark suite. There is a very, very good reason to do that sort of thing. I can guarantee you that I'm going to look at them very closely and will send you back any suggestions for improvements. So this will improve your applications. That's one thing. You will get free consulting in some sense. The other reason is that hopefully these benchmarks will drive the development of Erlang OTP for the next few years. So if you manage to put your needs there, chances are that the OTP team and or the release partners will be doing something good for the needs of your application in the years to come. Thanks a lot. Yeah.
So how much, let's say you could change other portions of the overall environment that you're working in. Change the operating system, change the chips, change the memory, you mentioned cache. Like, if the whole system end to end was, changeable, what would you say are the bottlenecks?
Where?
If you could change anything, what would you change to try to get to a 64x?
For Erlang, one of the things you definitely need is a machine with a lot of cache. So the cache that you have in your machine plays a very important role. So if you want this is a machine that does not have a lot of cache per core. It's actually a Each chip has 16 cores, and it only has 12 megabytes of shared L2, and another, unfortunately, only 12 megabytes of L3 cache, which is shared among everybody. So the cache here is killing us. So the number one thing I recommend for good scalability and performance is machines with as much cache as you can afford. On the i7, which has a lot of cache, the speed ups are much better. Yes?
The NUMA stuff matter much at all? The non-uniform architectures?
Obviously, it matters. How it matters, I have not investigated so far. Jay, you had a question.
You talk about Erlang OTP, but everything seems focused on Erlang. How much are you actually focusing on OTP things in this effort?
Well, actually, as part of parallelizing dialyzer, we had to use some gen servers. And we have a global coordinator that actually gives tickets. And we had to do that sort of thing actually not for performance. We make the performance worse, but we had to do it so that we don't generate all the processes at once. And we have a good bound or some bound at least on the number of memory, of the amount of memory we use. Yes, last question perhaps.
What's a good benchmark for this? Like, what are the characteristics of benchmarks to have for it to be useful?
Something that can be run on its own. It doesn't need an exotic database or some hardware that only you have in your environment. And something that has a lot of processes, hopefully more than 64, because if you only have 42 processes, you cannot expect more than a 42 speed up. So something that has a lot of processes and it can be run just by pressing a button, saying, bench. That's all.
Ideally with some distribution as well.
If you have benchmark with distribution, obviously we are very interested in those too. And this is the next step. For the time being, for practical reasons and because I don't have that many 64 core machines lying around, we are only concentrating for the time being in machines with a lot of cores. But we will go. When we port to the blue gene, we will go to many nodes, definitely. And we do have now clusters of machines that we can run these things. So please buy me a beer and send me benchmarks. Not necessarily in that order.